Okay, now for our new function and for our new curve, we've figured out how far we go as t changes by delta t as a function of t star, as a function of t if we wish. Okay, and now delta s is then going to equal our vector delta s is going to equal our unit tangent vector times delta s. Why do we need the vector delta s? Well, we're calculating f dot delta s, the vector f with the vector delta s. Okay, what's our unit tangent vector? Okay, well, our unit tangent vector is going to be the derivative of this divided by its magnitude. We didn't have to worry before about dividing by the magnitude because we were on the unit circle, and the way we had parameterized it, the magnitude of the t vector, the derivative of the r vector was 1. Okay, but now the derivative of the r vector is not necessarily 1. Matter of fact, I think it's never 1 for this function. So, the magnitude of the derivative. Okay. So that's going to be what? R prime over the magnitude of r prime, that's how we get our unit tangent vector, times our delta s. Okay, now we know what delta s is. It's this, so we don't have to work that in until we absolutely need it. What's the derivative of our r vector? Well, this is our r vector, and this is our r vector in terms of t, and r prime is in terms of t. So that r prime is going to be two cosine t of I plus 3 sine t of j over its magnitude, which is a square root of, well, just the same expression as this, it turns out. It's 4 sine squared of t plus 9 cosine squared of t. And since we're talking about a specific interval, we'll use t star. We're evaluating this at our sample point, and that's multiplied by delta s. Well, what is the result of multiplying our unit tangent vector by our delta s? It's simply that we end up with the vector 2 cosine t star I plus 3 I didn't do my derivative here correctly, did I? I just wrote this down, looking at this out of the corner of my eye. I'm going to correct that. I'm not going to go off screen and correct it. I'll just correct it right here. Okay, it's going to be negative 2 times the sine of t star plus 3 times the cosine of t star. And then times I and j times delta t. Okay, what happened to this? Well, same thing that happened to this. When I multiply this by the delta s, I'm multiplying this by this, and this square root in the delta s is the same as the square root we have here, so it goes away. Do a firmer line of demarcation here. Okay, so it's this expression. So what's f dot delta s? Think about it. Okay, you've had a chance to think about it. Our f on our specific interval is the same as it was over here. So that's cosine squared of t star I plus cosine of t star sine squared of t star j dotted with our delta s, which is just negative 2 sine t I plus 3 cosine t j times delta t. And these t's are t stars because we're again looking at a specific increment or subinterval of our partition. Okay? And the dot product is clearly very easy to calculate. We're going to have cosine squared t times negative 2 sine t. So it's going to be negative 2 sine t star cosine squared t star plus what? 3 cosine times sine squared is cosine squared t star sine squared t star epidemic of not being able to give myself enough room, but that times delta t. So that's our f dot delta s. The sum of our f dot delta s is calculated just as it was over here, and it approaches, they're just written down the way it was over here, and again without going into the detail, it just approaches the integral, leaving myself enough room here I hope, from t goes from 0 to 2 pi because that's the interval we partition, of and again, didn't leave myself enough room. And I'm actually going to try to teach myself a lesson. And I hate to do this in your time. You should see where we're going. I just needed the dt on that. So if you see that, you should be okay. I need to get rid of that 2 pi as well. Forgive me for wasting your time here with, this is one of the reasons I usually use a prepared board. And now that I've got enough room, I'm still probably going to fill it up. Okay, that's a dt in there. I squeezed it in. That's our integral. Now that integral, if f is our force function, is the work done by that force as we go around that circle. This integral, this sine squared t can be expressed as 1 minus cosine squared t. If we then let u equal cosine t, we'll have a cosine squared t, which is a u squared, and over here we'll have a cosine to the fourth, which is a u to the fourth. What we won't have is stars on these t's, because we've done the, let the increment approach 0 and the stars go away for reasons you should understand, as I say. And then, yeah, we do have a complication. Okay, I was going to say we don't have a factor of sine t in here. If we could factor out a sine t from all of this, and we can, okay, we could factor out one of these of the sine squared, but then of course we wouldn't have a 1 minus cosine squared. We'd have a square root of 1 minus cosine squared. Factor out the sine and let u equal cosine. We're still going to get an expression in terms of u, and the sine t dt would then be our du, and we would be able to integrate. And the integral would be just a little trickier. But be still techniques that we learn in first year calculus, okay? And I'm not going to do the integration. I want to focus on how we set up a line integral and what it means. Okay, so again, this integral represents the summation of all the f dot delta s's if we break this curve up into little tiny increments. Now it was t that we broke up into little tiny increments, but that's going to give us little tiny increments around our curve. And on each increment we have a force, an f vector, depending on the position in the plane, and a t vector depending on the direction of the curve at that point. And we do the f dot t, a tangent vector corresponding to every point. We do the f dot tangent vector to get the component of force in the direction of the tangent, and we multiply that by the delta s. This is what we end up with if we do that process and take it to the limit. And this would be the sum of the f dot delta s contributions from each tiny increment.